This picture is from 1912, a publication, a scientific publication in 1912 that's talking about the link between fossil fuel combustion and the subsequent release of carbon dioxide and changes in atmospheric and global average temperatures. I want to pause right here, just with groups together. Let's look at these couple things together. As we think about the amount of solar radiation that comes from the sun and strikes the earth, it has three destinations, and I'm giving you these percentages here. 51% of that solar energy goes one place, 30% goes another place, and the remaining 19% goes another place. Here's the two things I want you to do. Try to assign the destinations that you think. And then I also want you, just as an independent exercise, to think about, well, what is one noun and what is one adjective, a describing word, that I think of when I give you the word greenhouse gases. Let's take a couple minutes here, think about the destinies in a small group of people next to you, and think about one word with the people next to you as well. We'll take about a minute for this. Yeah. 51% goes somewhere, 30% goes somewhere, 19%. You guys are doing things and then you're way back here. Don't miss it. No, the sun's light is pumping towards the earth. 51% of that energy goes one place, 30 goes another place, 19 goes another place. Yeah, I think so. I think it's pretty Get in this shirt. All right, here we go. Let's start with the words. Let me start with the words. Somebody give me a noun. If I say greenhouse gas, give me an associated noun.
Carbon dioxide.
Carbon dioxide. Beautiful. Somebody give me another one. Let's see if we can get to three. Yeah. Radiation. Okay. Give me another one. Yeah, Campbell. Solar radiation. Jack? Global warming. Fantastic. Tell me a little bit. Give me an adjective. Let's see if we can get three new people. Yeah. Bad. What else? Yeah. Hot. What else? Harmful. So the nouns, we've got some things. I know you've heard about this issue before, so we've got a couple compounds that we're thinking about, but on the adjective side, we got two words that are negative connotation and one word that's kind of in the middle. Let's dive in here and look at the percentages and see what we came up with. This graphic in the text, Mr. Hava and I were talking the other day. There's not a lot of figures in the text that we really like, but this one is one of them. This is a fantastic diagram. But what it shows you is the solar radiation that comes from the sun, 93 million miles. It finally strikes the earth, and that energy goes to about three places. Some of it is reflected off of the clouds in the atmosphere and atmospheric particles and bounce back into space. Some of it is absorbed by the surface of the earth, and some of it is absorbed by the clouds that are in the atmosphere. These arrows here are somewhat proportional to these that I gave you here. So when you look at this energy, the smallest amount gets reflected and bounces back into space. The 30% gets absorbed by clouds and other atmospheric particles in the stratosphere, and then the biggest section is absorbed by the surface of the earth. Let's continue. This is just a brush up. We're not going to watch this video here, but you may remember we were outside way back in August. If you can't remember about radiation, convection, and conduction, you'll have access to these slides and look at it. Queued it up right at 6 minutes and 30 seconds. It goes for about 10 minutes. At that time, we explained to you that the solar radiation itself, it doesn't have heat properties. The heat comes from the energy that goes into items on the Earth and excites a whole bunch of electrons and releases that energy in the form of heat. That is where the heat from the planet comes to. Let me toggle back here for 1 second because I want to bring something up. When we look at this, so now we can think about this in a new way, and I want to point out this red arrow. The amount of heat is absorbed by the energy is absorbed by the Earth and released in the form of heat. So all these bad things that we've been saying, Earth is a beautiful planet. It's very unique. And it has a range of temperature that is favorable for the inhabitant of many species. Without greenhouse gases, this planet is uninhabitable. They play an extremely important role. So we have to think about the connotation of greenhouse gases first in a positive light because of the benefit that they provide to the Earth and their ability to allow species to survive and thrive and flourish here. We have a nice fundamental niche. But when we add more to that, that's where we're going to see a problem. Let me go forward a little bit further. I have to go quickly on some of this. I wish we had more time that we could spend. It would be appropriate because of the gravity of the issue to spend an entire year making sure that people really understand. But we want to make sure that it's calibrated to the scope of what you truly need to know. And so everything today has been distilled down to the most important things. You're going to see the word key on a lot of these slides. So here, let's watch this video for a second. Only a couple minutes. And all the important stuff is going to be in words here. There's no narration. This information in that video is not new to you, unless you've been living under a rock, and even then it's probably not new, because under that rock it's probably getting a little bit hotter because of this effect. But let's look at it a little bit and break it down. So we have the electromagnetic radiation flowing from the sun to the Earth, and then heat is going from the Earth out into the atmosphere. That's conduction as we go from solid to gas. And then what's nice about all of these videos, and you're going to see this trend in all of the models and a lot of the videos and a lot of the data sets, they're going to show seasonal variation because air particles in the convection currents move around all over the planet. We've studied that to exhaustion way back in the second unit of our time that we spent together. So you see this movement, and they're showing air particles moving from here to there. Part of what I want you to understand about that is the global ramifications of one issue that's started in one place will not respect geopolitical boundaries. The air particles move all over the planet because convection currents are moving that at high speeds up into the atmosphere and around Hadley, Farrell, polar cell, etc. So we see that sort of thing. But the big question that we have is we already know that seasonal variation is a thing. We understand the patterns and the movement of heat energy from radiation to conduction to convection. But what you're seeing right now when we look at this data from 2016, which was one of these big data pushes to release this information, and you saw in this video, is this a trend or is this an anomaly? In order to understand, what do we have to know to interpret whether it's a trend or whether it's a blip? We have to understand, Gary said the past, I'm going to frame it as we have to understand more of the data set. Let's take a minute here to look at this. This is going to play on repeat. Here's what I want every person to think about. Each circle is 1 year of data. Here is January, February, so on and so forth around. This is the global average temperature per year. So right in the center would be what we determined the global average to be across a large set of time. And then out here is So this is 0, the red circle. The reference here is 1.5, and here is 2.0. Here's what I want you to think about. What trends do you observe by season or month? Because we know seasonal variation has something to play. And then what are the trends across a longer temporal time period across years? We'll watch it for a couple rounds here. Bless you. Okay, let's start with the seasonal variation piece. What would you see if there was a lot of seasonal variation across our planet? Keeping in mind, this is a global average. What would you see with the line in this radial diagram? Yeah. We'd see spikes. We actually see a couple spikes here and there. But do you think seasonal variation is a large factor when we're determining global average temperature? Taking temperature readings all over the planet. Does seasonal variation seem to have any trend to it? The trend would be that it's flat, right? Or there is no significant trend up or down across different seasons. What about across by year? It's the obvious thing, not a trick question. Yeah. Every year it's expanding and it's moving outwards. So, yeah.
So is there a reason there isn't a huge seasonal disparity in temperatures? Because even if, like, in the northern hemisphere, it gets colder during December, it's going to get warmer.
Exactly right. Did everybody catch this? That's a great statement there. When we're talking about global averages, when it's spring here, it's fall in the southern hemisphere because of the tilt in the axis of the Earth and all those things that we learned about in the fall as well. So when we're looking at global temperature, it's kind of normalized across all the places in the year because one season at one point in one area of the Earth is the opposite season in the other hemisphere. One thing I want to point out here is the year that we started collecting this data in a real diligent manner is the year 1880. So this is our best look at the data. This is looking at the data directly. We have measurements that we took, and we can look and record those measurements starting in the year 1880. So we feel really good about this data set, but let's look at it in a different manner. So I want to show some clustering of some data points. So we take data every given year, and if we look at it in small sets. So here's that same data again. This is temperature anomalies, so we're looking at spikes where we find temperature, it's slightly different than what we saw before. Instead of global averages, this is when we find abnormalities in the temperature. And this scale is 0, so this is right on par. Where we find temperature anomalies where they're higher than normal, they're going to be north of the dotted line, and lower than normal, they're going to be here. And this is years going across the category axis. So here, if we just look at one clustering of the data point, this is what we see. What can we conclude by this cluster? It's a little bit colder, and we have a bunch. So if we just look at this, it tells one story. If we look at a different cluster, a different story. Let's see if I can get this here. So here's a cluster from about the year 1955 through the year 1970, right in the middle. Here's a cluster getting a little bit closer to us, near the end of the millennia. This is what the full data set looks like. So when we're thinking about this data, more data is going to be advantageous to help us understand, well, what are these trends? As we address that big question, is this a trend or is this an anomaly? The only way we know is by looking at more data. Here's what the full picture looks like. So if I draw a bunch of trend lines, statistical trend lines, just looking at certain clusters, we can see where the data is going. The black line is across all of the data. The red is from here to here, green is from here to here, and blue is that little section right there. But what we see is a logarithmic exponential trend happening. The data that's the closest to us happens to be trending up the most. We have the most steep incline here. So we're looking at the whole picture, but we're also looking at the data that's closest to us to try to understand. Those other questions are just for understanding the how do we collect we'll look at here in a second. one thing that researchers have posed and people in the public have thought about, how do we explain? So we've seen the data. The data is pretty sound. There's no interpretation or bias around the data. We've put thermometers all over the world and we measured it, and we can see things are without a doubt from the year 1880 till now, things are getting hotter. That story is pretty sound. So now we want to try to understand what is the connection or correlation. One of the things that has been posed out there is maybe it's irregularities in the nuclear reactions that are happening in the sun as they produce energy and pump it towards the sun, towards the earth in the form of photons. So here's what it looks like, solar radiation. Just look at this graph right here. Here's those same years. This is the amount of solar radiation. We have some spikes, but we have a lot of variability and a lot of movement up and down. Here's the other graph again, same data set that you just saw. Here's the years, here's the temperature. When you look at these two factors, this variability in solar radiation and changes in the chemical reactions that are happening in the sun, does there appear to be a link to you? Campbell? No. Give me a little bit. Walk me through the analysis. Somebody else, give me a little bit more on why. Morgan? About the year 1960 is a peak.
Yeah, it seems like from there it's gone on, whereas the global temperature is
So we have global temperature significantly rising here, but the amount of solar radiation, if we could even draw a trend across all that roller coaster, would maybe be trending down, if anything. So there doesn't seem to be a match. So we have to look for something else. Key. I want to watch this video and I want to think about something. We started measuring data all over the world, trying to look and understand the mystery. Here's a couple things that I want you to think about as you watch this video, which is only a couple minutes. We're thinking a lot about the data, about the collection of the data, because the scope of the data is so large. So I want you to pay attention to how we collected this data, but I want you to think about how we understand it. And as you look at this, we're looking for a few factors. You're going to see some abnormalities and a little bit of explanation. But I also want you to think about, well, what other information do we need to know in addition to this to help us paint a full picture? This terminology here for the Keeling curve, which is what the video about, is a key term in this unit. Here we go. we're going to break this data, this information down in those 3 parts, and then I want to talk about a few specific things. This video will be worth a second watch in your independent study, by the way, because there's a lot going on to try to interpret. We have this seasonal variation piece. We have some trends across time, across a whole bunch of years, and then we're trying to match that up with the global average temperatures and see if there's some type of trend. We'll talk about some chemical elements that will hopefully make sense of this too in a couple slides. So if you're wondering about carbon dioxide and its heat capacity thing, hang on, I'm going to get there for you. All right, so the data challenges, they're pretty huge because we have to measure this out in the atmosphere. It's not insignificant, the amount of instrumentation and the amount of discipline that you have to measure a single data point a bunch of times a year for decades on decades on decades. It's beyond the capacity of one person's work to be able to do. So now let's think about how do we understand the data, and I'm going to go forward to this next slide, and we're going to try to match things up together. So in your mind, as you think back from a slide or two ago, we saw the solar radiation with a whole bunch of variability, and then side by side was the global average temperatures. Here's a new graph. This is global average temperatures again, but I just wanted to show a more recent data set that showed what things look like so you could see some air bars. We have much better data. It's from the year 1990 on. And here, so here's 1990 on this graph, here's 1960 when we started this. This is the concentration of carbon dioxide in the atmosphere plotted against number of years. How do we feel about, oh, I'm sorry, this is emissions, excuse me, I'm sorry, I have another graph here in a second. But the air bars here is associated with emissions from vehicles and other sources that produce carbon dioxide. So what we see is the amount of carbon dioxide on our planet, as measured here at the observation in Hawaii, the observatory there, is going up. At the same time, the amount that humans are producing, which is the emissions piece, is also increasing. I feel like there's a lot more that we need to explore to fully understand this data. I looked it up this morning, by the way, and on this date right now, which you can go directly to the website, we're at about 412 parts per million of carbon dioxide today. So now we see a match between these two things. I want to try to understand that healing curve part where if we look back here, let me zoom in, we're going to do a little work here. So we see the overall trend is going up, but we see across any given year, the carbon dioxide goes up, and then it goes down, and then it goes up again. With each subsequent year, the peak getting a little bit higher, but how do we understand that up and down? Let's dig into that a little bit because it's really important to understanding how the Keeling curve is assembled. On this video, which is also really short, you're going to see the data set shows the red and purple are the amount of emissions. So it's kind of a heat scale, and then the blue is a lack of emissions. What I want you to pay attention to here is where's the concentration, so the spatial effects across our planet, and thinking about it, how does it change across time?
2014 is shaping up to be the warmest year.
Warmest year ever recorded for planet Earth.
Pause it here for a second so we can see what's going on here and make a couple notes. We've seen one other effect associated to what's here on the screen right now. It says America's coal-fired power plants, are mostly in the Midwest. That's where we're producing a lot of electricity. Where did we see that before? We literally just talked about it within the last couple days. What was it? Not quite smog, but you're close. Smog is more like associated with cars driving photochemical oxidants being produced. What are we talking about? America, yeah. Air pollutants, which ones specifically? Carbon dioxide would be one as we produce fossil fuels. That's one of our focuses today. Two others, and I'll give you a hint. They're must-know ones, yeah. Carbon monoxide, close. Sulfur oxides and nitrogen oxides being produced. So you're going to see one of the spatial effects is shown here as well. As these coal-fired power plants combust coal and use it to produce energy, we have a number of emissions being made. The focus of this is carbon dioxide, but at the same time, we're producing sulfur oxides and nitrogen oxides that make acid deposition. Watch where it goes. Watch where it goes. Here is this right here is showing emissions from cars, like photochemical, so in areas where there's a lot of driving. So that's also noted as well. Let's keep going. Look at the season of the year here. So it showed that peak emissions are at this time of year. Look where they're at. So most of this carbon emissions are happening in the northern hemisphere. The time of year in early spring, late winter is when carbon dioxide is at its highest levels. That's the peak of the Keeling curve. Why is that? Let's pay attention to what they're saying here. Check out how this picture now compares to the other. The carbon emissions are the amount of carbon dioxide in the atmosphere. We barely see any red now. We're in the middle of summer. What's true in the middle of summer in the northern hemisphere? What's going on in the ecosystem? Plants. A lot of productivity, a lot of sunlight. Favorable temperatures for plants to thrive. What do plants do? They suck up a lot of carbon dioxide from the atmosphere. Let's keep going. I want to pause it right here and point out a couple things. So now we understand a little bit more about the Keeling curve. When plants are highly productive, they're taking in a lot of carbon dioxide, and the amount of carbon dioxide in the atmosphere, as a consequence, goes down. But when plants aren't productive, especially in the northern hemisphere, in the boreal forests of Canada, which is the most productive ecosystem in terms of taking in carbon dioxide during the winter there, the amount of carbon dioxide in the atmosphere goes up. Across time, the amount of plants we have hasn't really changed. But what has changed to account for the amount of carbon dioxide going up? What do you think? Look at this graph right here. So here shows across a larger amount of time, which we're going to explore how this data set was created in a moment. But this is 400,000 years ago. This is the beginning of our species. This is carbon dioxide levels. Here's where we're at right now. How do you account for the difference in carbon dioxide? What do you think?
Well, consider that that's another species that we live that long that shut.
So we really breathe a lot of carbon dioxide via cell respiration, right? What do you think it is? It's emissions. We just saw emissions. We just saw a data set that showed places on the globe where a lot of carbon dioxide is going out into the atmosphere. These satellite images. And they happen to be right over the spot where carbon dioxide emitting coal-fired power plants are. Seems easy to measure. All right, let's keep going. Let's keep going here. I want to pause here and think a little bit about the chemical agency related to these molecules and a little bit about greenhouse gases specifically. So here's a plot. This graphic is really good, 19.1 in the text. It's worth a reference at this point in time. But what we see is not every compound is capable of holding heat energy. Some compounds hold it better than others. And some molecules break down on different timelines. So basically what we're saying here is the same thing from the first slide that I was bringing up. We have solar radiation going into the earth, then conducting that heat energy, and then convection cycles swirling it all around. We've just seen a lot of information about that. So that's how we end up with heat in the atmosphere, and that's how we hold heat in the atmosphere. Our atmosphere is made out of about 80% of nitrogen, triple covalently bonded together. It's not bioavailable, a little biogeochemical cycle throwback right there. A little bit of diatomic oxygen, atmospheric oxygen, O2, and then a whole bunch of other stuff. Neither one of those molecules, nitrogen, N2 or O2, are particularly good at holding heat. So the 2% of the other molecules that make up the rest of our atmosphere are the ones that are really good at holding heat. This is what they are. Carbon dioxide, this is a little hard to read, I understand. It's a lot of the same ones here. Carbon dioxide, methane, CFCs, ozone, nitrous oxides, and then we'll also mention water vapor. So these make up the remaining 2% of the atmosphere. Carbon dioxide is one of the best at holding heat. 56% of the heat energy is retained and absorbed by that molecule. 18% for methane, 13% for CFCs, 7% for ozone, and 6% for nitrous oxide. So as we look at the functioning of our planet, and it's breathing as plants take it in and it's expelled by animals, and now we have this emissions piece as well. Most of the heat energy that exists on our planet exists because of carbon dioxide and its ability to hold heat. And it's not even that much. We're not talking about a huge proportion of the atmosphere. It's like a fraction of a percent. So as we increase this, it has a dramatic effect. I just want to mention here that its breakdown, depending on where it's at and some other factors, it can exist in the atmosphere for a long time. So once it's produced, it can stay out there for an extremely long time. Likewise, chlorofluorocarbons that not only hold heat but break down the ozone hole, as we talked about last time. That's an important mention as well. So I want to pause here and hold on to this slide because we're going to start using a lot of words here. But I wanted to give you all the elements of the puzzle so that we could try to understand this a little bit. Number one is greenhouse gases are extremely important. What are the greenhouse gases? You just saw them. But the most important one is carbon dioxide. Under normal functioning, it plays a key role in our planet. As we increase the amount of carbon dioxide, we have more more compounds that can hold heat energy, and these emissions are producing more and more, and they're going out into the atmosphere, and it's holding on to these elements. Now, here's the piece that I feel like we sort of understand the link, hopefully, between temperature and carbon dioxide. We're going to deal with this a little bit in the laboratory setting starting tomorrow, and we're also going to deal with it in a data setting a little bit. But I want to make sure one thing is really clear on this slide. We're going to talk a lot about global change, and it isn't always heat. Heat energy powers climate and weather, and it moves everything in our atmosphere. Again, if you need a refresher on that, go back and watch the lecture from August. I explained it pretty well, I hope. But the idea is, the way that we move and do everything on our planet is through heat energy. And so if we increase the amount of elements and compounds that can hold heat energy, we can have a lot of changes. So global change could just be any sort of change that's happening across our planet. It could be biological. It could be physical properties of the planet. It could be chemical properties. Global climate change refers to just the changes in the climate. And global warming refers to just the warming, just the temperature changes that are on land masses and oceans and present in ecosystems and atmospheres of the Earth. There's a connection between all three of these, but they're definitely not synonyms. So it's not just the increased heat energy, it's the changes that are associated with adding more heat energy to our system. This is how we're going to end it today. And I want to make sure that everybody does this exercise as a throwback to biogeochemical cycles, but trying to understand all the elements of the carbon cycle. So let's think about this in individual groups. I want you to try to go through and fill out what forms do we find carbon in all of these places? What role does it play? So we're going to have, when I say what form, I mean what chemical form. Is it CO2? Is it CH4? I want to know a chemical form. And what role does it play for each? And where does most atmospheric carbon go? Where does it come from? And where does it go? Both think ecologically and the impact from the human element. This feels like a really great free response sort of question here. A little bit back to biogeochemical cycles. Let's take a couple minutes to work on this as we round out the day.